everyone. Thank you very much for giving me this chance to introduce my work. So my talk is about the unstructured prediction using the deep learning method and the statistical force field method. Here is the outline. For this CASP15 we have prepared two methods. One is deep learning method, it's called the row fold, and the other is the statistical method called the break. So in this talk, I will introduce the overall architecture of the row fold and the basic ideas of the break, and then I want to make a comparison between the statistical force field and the classical molecular force field. First, this is the architecture of our row fold. So the architecture is learned from the AlphaFold 2. But for the RNA case, we have a big challenge. It's the insufficient structured data. As we know, the structures in the PDB of RNA is much smaller than the protein. So to make full use of the existing data, we introduced a new module called the foundation model. So here is our RNA foundation model. This is a language model. We use only the sequence informations. The model is trained on the non-coding RNA sequence database, and it can output the representation of every of the input sequences. So this foundation model can be combined with the MSA to extract more evolutionary information. Here is a simple test of our foundation model. We can extract the sequence pattern information, and we can discriminate RNA families. But the overall performance, the result is not as good as the AlphaFold 2 to the proteins. The deep learning method is not the best performing method in the CASP15 RNA, but is comparable to the other top groups for these 6 native RNA-only targets. Our model failed at the 4 synthetic RNAs, maybe because we have no MSA and no evolutionary information for these targets. Here's a simple conclusion. So currently, our deep learning method didn't outperform state-of-art structural model methods, relying on structural sampling on scoring functions. So this result is a bit different from what we saw on the RNA puzzle test before the CASP. We are wondering the reason. It may be because in our puzzle tests, we're using 18% sequence identity cutoff to divide the training set and the test set. But this cutoff may be not strict. For example, for our RNA target 1117, we found homologous model in the PDB database is the 34U2. So these two structures, or these two molecules, has a sequence identity only 15%, but the MSD is 2.6 angstrom. According to this criterion, the 17% sequence identity cutoff, we cannot remove all the homologous structures. So that's maybe the reason we saw a better result in the puzzle test than the CASP. So besides the deep learning method, we have another way to do the unstructured prediction. So it's a statistical energy function strategy. So we are trying to learn physics from the structured database using statistics. The principle is very simple. It's the reverse Boltzmann distribution. And our objective or our aim is to build an ideal energy function, which is accurate enough and not a consequent model and not an atomic model. So we want an electron cloud model. And meanwhile, I want the energy landscape be smooth and so it will be good for our structure sampling. And to achieve this goal, we tried several strategies. I think the most important thing to build a connection between the structure database and the physics is do the probability density decomposition. To understand this idea, I use in this example the distance distribution of leucine C-delta atoms. The blue line is the observed probability or observed distribution. But this distribution consists of three different kinds of contacts: the direct contact, the indirect contact by bonding, and indirect contact by packing. So the black line is the distribution for the direct contact. Only the direct contact has a strong relationship with the real physics. Here, as you see, this is the distribution for the direct contact. It's a single peak distribution. And from this distribution, we can get an optimal packing distance for different two atoms. And from this distance, we can calculate the packing radius of different atoms. And if we extend the one-dimensional distance to three-dimensional, we can get the packing radius of different atoms in different directions. So using this information drawn from the direct contact, we can draw the electron cloud surface of different chemical groups. For example, here is the surface for the leucine C-delta atom, and this is the surface for the phenylalanine side chain groups. And if we extend this idea to the polar groups, we can see something more interesting. For example, if we place the glutamine OE atoms in the local frame of phenylalanine, we can get this distribution. If we turn this distribution to a density hot map, we can see on the horizontal direction, it has a higher density. On the vertical direction, it has a lower density, which means that in the horizontal direction, the charge is positive, and in the vertical direction, the charge is negative. So this is consistent with our quantum mechanics. And similarly, if we extend this idea, if we put the ribose O4 prime atoms in the local frame of base adenine, we can get a specific distribution. So we can convert this three-dimensional distribution to a statistical energy function. So, and this is our 3D energy. For the base-base interaction, so it's more complicated. To describe the interaction between the base, both for the base pairing and base stacking, we need a 6-dimensional energy to describe the orientation effect. So we take a strategy. First, we divide the orientation space into 9 billion conformations, and we calculate the about 5 million effective conformations, calculate their energies, and using the combination of the density estimation and the quantum mechanics. And these pre-calculated energies were put into a hash table for our structure sample. So here is our sampling strategy. we're using a Monte Carlo strategy to do the structure sampling. First, we organize the ion structure into a folding tree. So each node of the folding tree is one base. So this folding tree, the connection of the folding tree can be a sequential neighbor or a pairing neighbor. So to do the structure modeling, we first model the structure. We first model the coordinate of the base, and then we add the ribbons, and then we add the phosphate. So instead of searching the structure space in the backbone dihedral angle space, we do the sampling in the base orientation space. So this is much more efficient. And for the real case, for example, our CASP targets are 1126. So we're using the strategy of motif assembly. First, we build a model of different fragments or different motifs first, and then we assemble them together and do a global refinement. So both the modeling of the fragments and the global refinement is using our statistical force field, the BRIC. So what I want to achieve, or what I want to build, is a force field. It's a statistical force field, which is comparable to the classical molecular force field. So our statistical force field has a very different architecture with the Amber force field. For treatment of the different interactions, non-polar interaction, polar interaction, and bonded interactions, we're using quite different strategy. And for the salvation, currently we haven't added the salvation effect to our energy function, which the Amber usually use an explicit salvation model, for example, the TIP3P or others. Our energy function is not differentiable, so we can only do the structure sampling using the MC sampling. But the Amber is differentiable, so they can do the molecular dynamics simulations. So here is the overall performance of our method. So using the GDTTS as the criterion. So for this synthetic analysis, we have a great advantage. And for other targets, we are among the top methods. So here I show some case. So first, this is very interesting target, the 1138. The EM model has two conformations, one young conformation and one mature conformation. We have a good model for the mature conformation. So it's very, very consistent. So of course, we do this, we first model the three pillars and then assemble them together and do a refinement. But the young conformation, we didn't make it correct. Our predicted model is more like an early stage of this RNA folding. For another target, the 1116, we didn't give the right topology on the upside because our energy function is not accurate enough to distinguish these two different topologies. So I think there's a long way to go to build a better or build an ideal energy function for the RNA structure model. So here is the acknowledgement. So thanks, Dr. Shen Tao and Professor Li Yu for their help. They built the deep learning model. And thanks, Professor Yao Qi, for the help of developing the BRIC energy function. And thanks very much for our Zelig Circle founders. That's all. Thank you.
Thank you very much.